The basic idea behind the dynamical friction is that a moving mass attracts objects to it, but because of its motion, the objects tend to gather behind the mass, pulling it backwards. To calculate the drag force, it is best to think of a single object passing the mass on a Keplerian hyperbolic trajectory, and then sum up the results of the many encounters. So let's consider this. A star or an object of mass m, big M, moves with the velocity v, big M, for a swarm of stars. The number density of these stars is n0, and their velocity distribution is Maxwellian, the velocity distribution of the stars. Due to gravitational encounters with these other stars, the trajectory of the star big M will gradually change. We want to estimate the rate of this change. For that, what we're going to do is find the results of individual encounters and then sum up the results of the many encounters. So let us first treat an encounter of two bodies of mass little m and big M, approaching with velocities v little m and v big M, respectively. We already solved this. This is a two-body problem. The equation of motion for the separation is given by, and if delta v little m and delta v big M are the changes in the velocities during the encounter, then the difference between these two deltas gives the delta v, the vector delta v of the system, where v is dot r. Now, if we find this delta v, then by conservation of momentum, delta v of the bigger object is given by minus little m over the sum of the masses times this delta v. What we need to do then is to find the delta v after the collision. So this is the problem of two-body scattering. So this is a routine celestial mechanics calculation, and it's well known from planetary dynamics. If you consider the two-body encounter to be a hyperbolic orbit, so I have the object in here, the mass, the object of mass big M, and one of the little stars. It's approaching with an asymptote b, and then there is this deflection. If you consider the equation of the orbit in the reduced mass frame, I have here P over R, where P is the semilatus rectum, do not confuse with momentum, and phi here is the true anomaly. E is the eccentricity, which for a hyperbolic orbit is bigger than 1, where big E is the energy, and big L is the angular momentum, and they're both constants. We find these constants then by considering the particle at infinity. At infinity, there is only kinetic energy, there's no potential energy. So the energy is simply v squared over 2, where v is the velocity at infinity. And the angular momentum then at infinity is the velocity of approach times the impact parameter. Let's consider the asymptotes then. We have that the body is approaching and with impact parameter b. The asymptotes are at an angle phi infinity, and the velocity is making an angle alpha with the horizontal. If you consider the equation of the orbit, which is this equation here, when r goes to infinity, then you have that this equation here, the right-hand side has to be 0. So the phi at infinity is given then by 1 plus e cosine of phi infinity is equal to 0. That gives you then the cosine of phi infinity is minus 1 over e. And the angle alpha is found by trigonometry, because the continuation here, this angle would give you phi infinity. So this angle is 180 minus phi infinity. So 90 plus alpha plus 180 minus infinity must be equal to 180. So we have this then, the alpha is equal to phi infinity minus pi over 2. So if you take the sine and the cosine of this, you have then the sine of alpha is equal to 1 over e, and cosine of alpha is equal to this. If you consider now that the orbit is symmetric, in magnitude, the velocity before the collision is equal to the velocity after the collision in magnitude. But in vector form, because the direction changed, you can write that v after is equal to v before plus a vector delta v. So let's break this delta v here in two components. One that is perpendicular to the v before, and another one that is parallel to it. So let's call this delta v parallel and delta v perpendicular. So there you go. You have that this component here, delta v, is a sum of a perpendicular component to v before and a component that is parallel to it. And geometrically then, we can find out what these components are. So for the perpendicular, we have a right triangle. So this is a right angle. The right triangle, this is the hypotenuse, that's v after, which in magnitude is v. And you have this angle here, which is 180 minus 2 alpha. So the delta V perpendicular is equal to the hypotenuse V times the sine of 180 minus 2 alpha, which is equal to the sine of 2 alpha. There you go. The perpendicular is equal to V times sine of 2 alpha. Now, the parallel one, if this side here is V sine of 2 alpha, then this side here from the perpendicular to the vertex is equal to V times cosine of 2 alpha. This whole vector here is V. So this little part here is V minus V cosine 2 alpha. That's what's written here, V times 1 minus cosine of 2 alpha. If we substitute the expressions we found for sine alpha and cosine alpha, then we find these expressions in terms of the eccentricity. Now, if we now substitute the eccentricity for its expression in terms of energy and angular momentum, substituting the energy and the angular momentum, this is the expression that we find. Here, these are the expressions for the energy and the angular momentum. Substituting here, energy is equal to V squared over 2, and angular momentum is equal to V times B. This is how this expression turns out. Substituting that value for the eccentricity into these two equations, then we have these expressions for delta V perpendicular and delta V parallel. So this is the delta V of the system in the reduced mass frame. As we said, if we want to find the delta V for the big mass, we have to multiply that by little m over the sum of the masses. So doing this scaling, these are the expressions that we get then. Now we can simplify this by noticing that g times the sum of the m's over v squared is the semi-major axis of the hyperbola, which geometrically is the minimum impact parameter. Let's call it b min. Now making this substitution, the change in the velocity in the perpendicular and parallel direction for the big mass become these expressions. So this is what we have in the end for a single encounter. The body is going in its trajectory. A single encounter is going to have a change in the perpendicular direction and a drag in the parallel direction. As you can imagine here from this expression, if you integrate over all of the possible impact parameters, because the impact parameter here is going to be a function of the angle, if you integrate over all angles, this is going to average out. So if you have several different encounters, if you have many random encounters, the first one is going to zero out. And there is no change in the momentum in the perpendicular direction. In the parallel direction, though, momentum loss accumulates like a drag force. So we will use delta Vm parallel to estimate the dynamic of friction. Now, the effect on delta V perpendicular is not negligible, though. The momentum averages out, but there is a random walk that results from all of the encounters, and that adds kinetic energy. So the system is going to get dynamically excited. The time scale of this injection is the time scale for two-body relaxation, which we will calculate now in the next video.